Hi, we're going to discuss the mean value theorem. So we're going to consider some function that is going to be continuous on the closed interval a to b and differentiable on an open interval a to b. The function may or may not be differentiable at the endpoints. That's not important. So continuity tells us that function has no breaks, and differentiability tells us that we're looking most of the time at a smooth curve. There are some exceptions to smooth curves, but we're not going to discuss this now. So we consider a function whose graph is given to us, and we draw a secant line through the endpoint. So we have an endpoint at A, which is right here, and this point on the curve that's going to go along with that, and we have an endpoint at B. And what we can do is we can draw a secant line through those 2 points. It's going to look like this. So the secant line represents, I want to remind you, the secant line represents the average rate of change, the slope of that line. So what can we infer from this? It looks like somewhere here there will be a tangent line that's going to have the same slope, that's going to run parallel to our secant line, right? I think it's visually easy to see that it is possible for a point like that to happen. So that would be this line. So we're going to have a situation in which the slope of the secant line through the endpoint is going to equal to the slope of the tangent line at some point on that interval a to b. That point of tangency here is going to fall somewhere between a and b, right? There's some point c. So that's essentially what we are going to analyze. All right? So the slope of the secant line is represented by f of b minus f of a divided by b minus a. The slope of the tangent line at some point c is going to be represented by f prime of c, and we claim that those two things will be equal, right? So what does the mean value theorem say? The formal statement is, if f of x is continuous on the closed interval a to b and differentiable on an open interval a to b, there must be at least one value x equals c. C is going to have to be between a and b, it says right here, where the slope of where f prime of c is going to equal to f of b minus f of a divided by b minus a. So this is the formal statement. In other words, there must exist at least one point where the instantaneous rate of change is going to equal to the average rate of change. In plain terms, there must exist at least one point where the slope of the tangent line is going to equal to the slope of the secant line. Okay, so that's what we are going to talk about. Let's take a look at our first example. For each problem is going to come, we're going to determine if the mean value theorem can be applied. If yes, we find the value or values of c that satisfy the theorem. Otherwise, we're going to explain why not. All right, let's take a look at this one. F of x equals x squared minus 4x plus 2 on the interval from negative 4 to 2. We know this is a continuous and differentiable function, right? But we do need to remember that we need to analyze that, continuous and differentiable. Right? So check, check. So what we're going to do now is we're going to find the derivative. The derivative, so f prime of x is going to be 2x minus 4. And we want it to equal to f of 2 minus f of negative 4 divided by 2 minus negative 4. So this is going to be 2x minus 4 equals f of 2 is negative 2, f of negative 4 is 34 divided by 6, which means 2x minus 4 is going to equal to negative 6, and x is going to equal negative 1. Let's check. Negative 1 is on the interval from negative 4 to 2, and this is our value of c. Okay, so in this case we can say c equals negative 1 just to be consistent with the theorem. All right, moving on. So f of x equals x squared plus 6x. It's another quadratic function. It is continuous and it is differentiable. Okay. It's continuous and differentiable everywhere, so we don't even need to worry about the particular interval. Alright, so what are we going to do? We're going to do f prime of x, which is 2x plus 6, and we want it to equal to f of 3 minus f of 0 divided by 3 minus 0. Okay, so that's going to be 2x plus 6 equals f of 3 is 27, f of 0 is 0 divided by 3. So we want 2x plus 6 to equal 9, and that means x is going to equal 3 halves. Is that point on the interval from 0 to 3? Yes, it is, obviously. So that is our value of c. Again, we can say, to be consistent with the notation used by the theorem, you can say that c equals 3 halves, but remember that c represents a value of x. Moving on. 1 over x. So we have to be careful. 1 over x, f of x equals 1 over x is not continuous everywhere, but it is continuous on the given interval. So continuous on the closed interval 1 to 4, check. Differentiable on the open interval 1 to 4, check. So we're going to go ahead and find the derivative. The derivative of 1 over x is negative 1 over x squared. And we want it to equal to f of 4 minus f of 1 divided by 4 minus 1. Right? So we want negative 1 over x squared. Let's figure out these values. F of 4 is 1/4. F of 1 is 1 divided by 3. So that is going to give us, all in all, after you simplify it, is going to give us negative 1 over x squared equals negative 1/4. That means x squared is going to equal 4, and x is going to equal plus or minus 2. Alright, so we get two values. We need to be careful, because one value is negative 2, and that value is not going to work because it's not on the interval. X equals negative 2, no. So we're going to have to reject it. But x equals 2 is fine. It is on the interval from 1 to 4, and that's our answer. Okay. Example 4. So we have a function f of x equals 2 over x squared. Our interval is from negative 2 to 1, and we have a slight problem here. This function is not going to be continuous on the interval. So the function is not continuous on the interval from negative 2 to 1 because it has a discontinuity at x equals 0, so the mean value theorem cannot be applied. I just want to make one comment with regards to this situation. That does not mean that there is no such point where that's going to happen, but because we have an issue with continuity, we are not going to be able to do that because the function must be continuous and differentiable. So if it's not, then there's nothing we can do, and we just say it's not possible. Okay, next function, f of x equals square root of x. On the interval from 1 to 4, this function is continuous on this interval, and it's differentiable. It is actually a function that's continuous and differentiable on its entire domain except the left-hand point. Differentiable. Okay, so we find the derivative. The derivative of square root of x is 1 over 2 square root of x, and we want it to equal to f of 4 minus f of 1 divided by 4 minus 1. 1 over square root of x, I'm sorry, not 2. Alright, so what do we have here? That's going to be 1 over 2 square root of x equals, that's 2 minus 1 divided by 3. So 1 square root of x, so we got 2 square root of x is going to equal to 3. That means square root of x is going to equal to 3/2, and x is going to equal 9/4. 9/4 is on the interval from 1 to 4, and that is our value. Okay. Example 6, so I got f of x equals x minus 1 to the power 1/3. You may recall that this function, I'm not going to get into the details now, but this function is not differentiable at the point x equals 1. It's going to have a vertical tangent line. This is actually a smooth curve, but it's not going to be differentiable at 1. And since 1 falls on the interval here, we cannot apply the mean value theorem. F of x is not differentiable on 0 to 2. Okay, specifically it's not differentiable at x equals 1, but as long as there is one point like that where we have this problem, there is no way we can use the mean value theorem, so the mean value theorem cannot be applied. Okay, and again, before you jump into setting things up and trying to figure it out, because in many cases you will be able to figure out the value despite the fact that the function may not be differentiable or even continuous. So before you jump straight into setting it up and computing things, take a look at the functions and make sure they are continuous and differentiable. Alright, here's an interesting problem where you can apply this. Not that the police does it, but a car is clocked by a police radar traveling on the highway at 65 miles per hour. Another police radar located 16 miles from the first one clocks the same car 12 minutes later traveling at 60 miles per hour. So at 2 points where they clocked the car, traveling at the speed under the speed limit. So everything seems to be okay, but the question here is, if the speed limit is 70 miles per hour, was the car speeding at any time? We're talking about comparing the average rate of change of the car with the instantaneous rate of change. So we have the distance traveled by the car in these 12 minutes. So what we're going to do is we're going to take a look at change in distance divided by the change in time. So what was the change in distance? The car was clocked 60 miles down the road, so it's 60 miles. What's the change in time? It's 12 minutes. Dealing with minutes versus hours is not going to be the same, so what we need to do is convert 12 minutes to hours, and 12 minutes in hours is 1/5 of an hour. And that's going to give us 80 miles per hour. This is the average speed of this car. Okay, so what do we know about velocity? Since velocity is continuous, because remember, if we want to use the mean value theorem, we got to make sure that the function that we're working with meets the conditions. So if velocity is continuous, the velocity is continuous means what? That means you're gonna, you don't have sudden jumps from like velocity of 55 to 57. It's gonna have to go through all the values between 55 and 57. So it's the velocity is continuous and differentiable. Velocity is a continuous and differentiable function. That means that we don't have sudden change in acceleration. Then the mean value theorem applies. Okay, and that means what? Therefore, there must exist at least one value where the slope, where the instantaneous rate of change which is represented by the slope. Is going to equal to the average rate of change. So what does it mean in our case? That means there's going to be at least one point where the car was driving at the average speed, which was 80 miles per hour. And it means, yes, the car was speeding somewhere. At least one time, right? So that's an application problem, a very neat problem. Okay, I got one more example and then we're done. So function f of x is differentiable on the interval from 2 to 5. Selected values of f of x are given in the table below. Explain why there must be a value x equals c on the interval from 2 to 5 where f prime of c is going to equal 2/3. So we don't have the function, we cannot differentiate it, but we know that the function is differentiable on 2 to 5. We're already halfway to meeting our condition. Since f of x is differentiable on the interval from 2 to 5, it's even a closed interval here, which is perfectly fine. It must be continuous on the interval from 2 to 5, right? Remember, differentiability implies continuity. And since we know that, therefore, the mean value theorem applies. How do we even know that if you were to see a problem like that not in the scope of this little lesson, how would you know that the mean value theorem might even be the case here? Here's a bit of a hint. You have an interval and you have a rate at some point that's going to equal to this number. So if you look, and you will see it in a moment, if you look at the statement here, there must exist a value of c where the slope will be a certain value. That might give you a hint that you're looking at potentially a problem dealing with the mean value theorem. So we're going to say hence, what needs to happen? We want f prime at some value of c to equal to f of 5 minus f of 2 divided by 5 minus 2. That means we're going to have, which is f of 5 is what? F of 5 is 1. F of 2 is -1, right? And that's going to give you 3, and that's going to equal 2/3. So we established that f prime of c is going to have to equal to the average rate of change. So by the mean value theorem, there must exist a point x equals c where f prime of c is going to equal to 2/3. Okay, and that's it.